All right, so last time we started iterative methods, or so-called indirect methods, for solving linear systems. They're going to essentially do less computations than Gaussian elimination, and because of that, they're not going to pile up as much numerical error. The problem with Gaussian elimination is that there is way too many, like especially if I have a very large system, let's say 1,000 by 1,000 or more, there will be so much computation involved that basically you will not get very accurate, even though you're kind of solving for a direct solution. So another way of solving these problems is to basically iterate the way we iterate to find roots. So first attempt is just to come up with some iteration that would hopefully lead to a solution. And one idea is to actually take, so here's an example 4x4 system, and basically I just take for every equation here, I isolate x1 and put everything else on the other side, and I get this equation. Here I isolate x2, put everything on the other side, and so forth. So technically I have, on the left-hand side, I have a vector x, which is supposedly the solution I'm looking for. And on the other side, I have a vector function of that same vector, right? So this is a function of x1, x2, x3, x4. Therefore, it's some sort of vector function of that vector. What does that remind you? Root finding. Does it remind you of one of the methods?
It looks like forward or backward elimination.
No, root finding method.
Several different ways to isolate x.
So this is one way to do it. So it's x equal to g of x. Remember that one? Okay. So I reformulated my ax is equal to b, which is same as ax minus b is equal to 0. I'm looking for a 0 of function called ax minus b. Okay. And I just kind of rearranged that so that I have x on the left side and some function of x. It's just that now I'm working with vectors. I'm not working with just one scalar anymore. Okay. So the idea is that I would just start with some x and try to iterate and get to a solution. Okay? And actually the method, so-called Jacobi method, Jacobi method is basically doing just that. So it's actually going to say, the only thing it looks more complicated because I have vectors and I'm trying to generalize this formula. So this formula basically generalizes, we went through it last time, it generalizes what I see here. I can see that for x1, I can see b1, right? For x2, I see b2. For x3, I see b3. For x4, I see b4. Therefore, I generalize that as putting xi here and bi. I'm dividing by a of ii for every of those i's. 1 over aii, right? And then this is a generalization of this sum here. This sum has every element basically of ith row of A multiplying vector x except for that ith term because ith term I isolated. So basically this is a sum from j to 1 to n, aij xj, okay, except for j is equal to I because that's what was on the left hand side. And then this k here is just telling me, oh, this is iteration number k. Now this looks cryptic, but because it's a single formula that is sort of identified by ij's k's, I can find a way to write code using this. Now before we write the code, let's actually just do an example and see whether it works. So take a piece of paper and let's try. So this is a system I'd like to solve. And I would like you, so this is copied from the previous slide here just as a reminder. This is a 4x4, you have a smaller system, you have a 3x3, so it's simpler. But first I want you to write this system, AX is equal to B, this system, I want you to write in this form. Just it's going to be 3 by 3. It's not going to have 4 by 4. And after you do that, let's try to iterate. Start with x0, so that my 0th or initial guess will be 0, 0, 0. And I want you to compute x1 and x2 vectors. And within these two iterations that you compute, let's see how quickly we get to the actual solution that is given right here. So I want you to reformulate this system in this form, and then start plugging x0 as 0, 0, 0, and try to find x of 2, basically using iteration, just like you would in the root finding problem with fixed point. It's just here you have a vector. Solve this. First one will be really simple to compute because you're plugging 0, 0, 0. So did everybody get to the part of isolating the equations or writing down the equations? So what is the first equation?
7.85 minus, within brackets, minus 0.1x2 minus 0.
Well, I'm just going to say plus then. Is that okay?
Plus 0.2x3 divided by 3.
Is everybody okay with that? What is the second equation? X, no, x2 is here. So I'm leaving x2 on this side. Right? So my second equation, my first equation is 7.85 plus 0.1 x2 plus 0.2 x3 divided by 3. Everything divided by 3. That's this. Right? So in the second equation, I'm going to leave 7x2 on left-hand side, and then I'm going to have minus 19.3 minus 0.1 x1 plus 0.3 x3 divided by 7, right? So that I have x2 is equal to something. And then the third one, I'll do the same. So it's 71.4 minus 0.3 x1 plus 0.2 x2 divided by 10. Cool? So now that I have it in this form, I can now create iteration. So I'm going to say, okay, if I have a previous step, which is step k at any given time, okay, then I plug it into the right-hand side, and my next step is given. So basically on my right-hand side, I have my next step, and this is all computed in terms of the previous step. So in terms of a vector, this is your x k plus 1 is some function, I'm going to call it g, upper G of xk. And by these I mean vectors, right? So it reminds of a fixed point iteration. Yes? Powers, or this is just, these are not powers, this is just next step versus. So this works for any case. So when I put in 0, okay, I'm going to have 1 here. So now plug in x 0, 0, 0, 0. So this is 0, this is 0, this is 0, right? What do you get as a first x1? So I want you to compute x1 and x2. This one is a function of x0, which is 0, 0, 0, so that one's really easy. And this is going to be the same function, but of x1. Yes?
Where do you plug in x 0, 0, 0?
To this, to right-hand side, 0, 0, 0, 0, 0, 0. And then compute what's left. This is a, so x1, x0. Where's mine now? Is a vector, and it's 0, 0, 0. This is x1, x2, 0, and this is x3, 0. As in third element first, second, third element of the vector. Okay? First, second, third element of the vector. So this is x1, 0, x2, 0, x3, 0.
By plugging those numbers, what are you obtaining?
You're going to get x1, x2, x3, 1 on the right-hand side as a next iteration. Right? So when I plug in, I'm going to have essentially 7.85. These are all zeros divided by 3 is my x1, 1. Yes?
How far do we keep going with that?
When do I stop iterations?
When your error becomes smaller?
Precisely. So we'll have to compute error. Right now we're just going to compute 2 and see how far we get. I have an actual solution there. So let's compute x1 and x2 and see how close we get. If you don't have a calculator, you have your phone. If you don't have your phone, you have a computer. Something that even Google makes conversations easy these days.
Wait, so for the next iteration, x1 is 7.85 divided by 3.
Yes.
And then
X2, it's minus 19.3 divided by 7.
isn't it like x1, like the left side, like x raised to 1?
Mhm.
Isn't that a vector?
It is. So it's going to have x1, x2, and x3. It's going to have 3 elements. That are, yes. Yeah.
Yeah, I get it.
All these ones, who is subscript, who is superscript, are a little confusing. Maybe I should call them new and old. Probably would be better. So take this as old and this as new, if that's easier to think about. So my x1, 1 is when I plug in zeros. What's 7.85 divided by 3?
2.62.
X2, 1 is minus 19.3 divided by 7. How much is that?
Negative 2.57.
Negative 2.57. And then my x3 is 71.4 divided by 10. Well, that one's easy. I can do that one. 7.14.
For the second one, I think it's negative 2.757.
Negative 2.757?
Oh, yeah. I heard only 57. Okay. So this is my vector x1, right? This entire thing, if you will. It's a vector. And this is its first, second, third element. Now, that's my first iteration. Now, same thing, I can plug in this, this, and this, x1, 1, x2, 1, x3, 1, to get x2 into this formula. Can you do that for me? That's a little more work. So I'm not going to do it on the board. I'm just going to wait for you to compute. So just plug in x1, this one, into this and get x2. So next step. And if you're done, compute error. This is your actual solution. Huh? Let me know how you compute error. These are vectors. If you're not done, just keep computing x2. Think about computing error. What would the error be for vectors?
U minus old over here.
What of mu minus old? Mu minus old is a vector. How are you going to divide it by old?
Divided by the vector.
How do I divide vector by a vector?
Transpose.
What is our measure of size of vectors? Not magnitude. So what is equivalent for magnitude or absolute value? What is the equivalent thing for vectors? Well, you can pick one. That's why we introduced norms of vectors. Now, you can also just request that every element, you can do element by element, and request that all of the absolute values of those differences divided by all are smaller than some epsilon. That's fine too.
So you just have to do absolute of the vector divided by the dot absolute of the vector.
Sort of, yeah. But then it should be less than epsilon on every element. So there are multiple ways of figuring out how far I am. Yeah. Did everybody compute x2 before we start discussing where do we stop? What is x2?
3.001.
3.001. Some
2.489
489.
and 7.006.
7.006. So how close do I look to this? Pretty darn close for iterating twice. Okay. So just a comment. So when would I stop? I can either go and look literally this element by element. Okay. Here I actually have a solution. It's given to me as actual solution. So I have exact solution. So here I would use exact solution, just like we do in computing errors for root finding methods. But if I don't have exact solution, which most of the time if I'm solving a problem, well, I don't have a solution. That's why I'm solving that problem. Okay? Then you would just take two last iterations and look at the difference. And you can do that element by element and make sure that for every element of a vector, I'm less than some tolerance. Or you can simply say, well, norm of this vector, you can just divide entire vector, like do a difference between two vectors and take a norm of it and then divide by the norm of the previous vector. So those are choices that you might have. So that's when I would stop. Questions? So again, it's similar to the fixed point iteration. It's just a vector now and a vector function, so that makes it a little more confusing to compute. But the idea is that I have my next iteration, the entire vector, is a vector function of a vector. Okay? So this is what I'm referring to as x is g of x. And then, of course, I'm wondering, this being a fixed point type of iteration, I wonder whether I'm going to converge. So in this case, obviously, in 2 iterations, I got kind of really close. So obviously, something's working. But it doesn't mean that it's always going to work. And we're not going to prove this or anything, but basically, there's one rule that tells me, I look at my matrix A, and there's a rule that tells me that I'm going to converge. And that rule says that if my matrix is so-called diagonally dominant, that means that absolute value of a diagonal element is larger than sum of absolute values of all other elements in that row. So let's actually, so this is basically, let's do it on a 3 by 3. So this says sum up all of the elements except the ith one. Ith one is here. So if sum of everybody except the diagonal element in absolute value is smaller than the absolute value of the diagonal element, then I'm diagonally dominant. Is this matrix 3 minus 0.1 minus 0.2, 0.1, 7 minus 0.3, 0.3, minus 0.2, 10. Is that matrix diagonally dominant? Everything is point something. This one was designed to be diagonally dominant. Off diagonal, I have point something, or numbers that are less than 1 in absolute values. And on the diagonal, I have 3, 7, and 10. Okay. So 3 is definitely larger than 0.1 plus 0.2. Okay. 7 is larger than 0.1 plus 0.3. 10 is larger than 0.3 plus 0.2. So that is sufficient to guarantee convergence of the Jacobi method. And when I say, but it's not necessary, that means that there could be other matrices that are just not visually apparent, okay, where this could be true. And for that, to actually check whether something is really going to guarantee, there is linear algebra theory that we are not going to go into because it's way advanced for this class anyway. So, has anybody heard of eigenvalues? So you would have to go compute eigenvalues and make sure that all in absolute values are less than 1. And that's an algorithm of its own. It's not something that you see the matrix and check. So it's a very important part of the theory. You do it probably in the FAQ. That's where it's important. But eigenvalues are important everywhere, pretty much. Yes, they are. Sorry. So you will get. So for instance, you will get to the geomechanics part in your life, and you will have a stress tensor. In subsurface, you have stress tensor because stresses are acting on you on all sides. And eigenvalues of stress tensor are the principal stresses in subsurface. And if you don't know principal stresses in subsurface, good luck to you drilling. And you have to know them every day. So, the moment you saw principal stresses, and there are 3 of them, the moment your pressure is above the smallest one, you're fracturing formation. So for hydraulic fracturing, yes, you need to know that principal stress. And guess what? That's an eigenvalue of the stress tensor. So eigenvalues show up everywhere. So anyway, I would have to actually check eigenvalues of the matrix and that they're all in that said, we don't know the stress tensor. We typically just actually find those principal stresses if we can. The smallest one is easy to find. The largest one not so easy to find. But their difference between the smallest and the largest makes it way more difficult to drill a stable well. Essentially, you can collapse the well really easy if the difference between those principal stresses is large. So that's just, think about that. When you think about eigenvalues, say it's not so bad that I need to know this. It's actually important for me as a engineer. You're just not gonna think about those stresses as eigenvalues, but it's important that they're there. Alrighty, so let's do some programming. Okay. Let's program Jacobi method. And this is actually a good practice for the test too, because this is really just a formula. I gave you the formula, and you're supposed to program it. Everything you need to know is actually on this page. It's just about writing the program and debugging it. And I want you to test it on this. So I'd like you to create a function called Jacobi method, or Jacobi iteration, apparently, according to my I'm going to say new function. I want it to be in a form of a function. So my output argument will actually be the solution. I'm going to call it x. And input is supposed to be matrix A, vector B, and starting point x0.
Would we always have x0 as 0, 0, 0?
You can, if you want to modify and just start from 0, 0, 0, sure. If you want to be more general, sometimes these things will not converge. And actually, how close you are. So, if you want to make that choice, that's fine by me. So he's saying, A, since I'm gonna, in all of my tests, going to type in zeros, I may as well do it within the function. There we go. And hopefully n equals to m. Initial guess.
Why did you create an NM matrix?
This is not a matrix. This is taking output of size function. Another way is to say n is size of A1. When I have a matrix, this is a review for test right there. I'm gonna type in this matrix that we're gonna use later anyway. When I say size of A, I get two outputs. 3, 3. Number of rows, number of
columns. If I actually want to immediately get number of rows,
then I can just do this. And in this case, both size 1 and size 2 as a number of rows versus number of columns are the same. So those are various ways you can do this. So this is sort of like your starting point of a function.
We should be able to go back to the page where you have x1, x2, x3, x4.
There it is.
I want you to write a general code.
Oh, in a for loop, can we do j equal to a certain range and then as well as j not equal to I?
And now you do test that with an if statement. Within for loop you have an if that tests whether your I is equal to j. So you'll need to compute this sum, so you're gonna have a for loop, right?
Yeah, I already have.
And then that, yeah, so then you say if I is different from j, add something to the sum. Write on a piece of paper first. If something is true, then do something. Otherwise, don't do it. So how do I just quick note? How do I conceptualize every kind of iteration? I have to initialize. What is my starting guess? I also have to initialize error, and I'm just gonna say it's 1, and I have to decide on some tolerance, and for the heck of it, I'm just gonna say this. So this is my initialization. And then every iteration will iterate while error is larger than tolerance, do something. So this is sort of like what you do in root finding methods when we had open methods. Now I have to just kind of fill in the rest. And within this while loop, you will say somehow you're computing this new vector x, which we can call x in this case, is some function of my x0, which is my previous guess. Then I have to compute the error between the two and update my x0, and that's essentially completing the iteration.
So my logical flow would be compute new x using the old one, which is x0. Then recompute error between x and x0 and update x0.
So what's here in green is essentially my logical steps in building any kind of iteration code. It works for root finding methods. It works for, this is essentially a sort of a root finding method just for a linear equation. Does this make sense or help, or did I just confuse you entirely? It's like, just make it verse. And so if I'm equal to, then this is like, so I'm going to do like, precisely. So if that is true, it's not equal, sum will be. Negative or negative is positive.
Ah.
Or positive or negative is negative. However it is. Where's your sum? Here, it looks like you're computing that sum. So then you're gonna compute this B of I, J times this number. You're gonna add it to one time. You're gonna overwrite this B of I. So you're not gonna have the sum. This sum. So you wanna compute X and J, right? Well, kind of reverse that. They wanna actually have some. So for every I, we first want to compute that sum, which is doing the sum. And after you do it, then you compute it. I would use norm using vectors, vector difference. So for error, any questions before I? We're not done thinking about error. I'm just gonna write error here whenever you're ready.
I'm just gonna say error is norm of your choice of x minus x0 divided by norm of x0.
That works. By default, what is MATLAB going to use? Which choice of norm not so important. If it converges, it converges. If it doesn't, it doesn't. You will be a little off in the operations, but otherwise. Initially, I might have a problem. Yes. Yes. Yes.
So this is a relative error, right? Wow. If norm
So it'll skip 0.
Where do we put this in though?
This is
Yeah.
right here.
we can just say maybe like this. Else still compute something, just don't divide. There in comment, this is one possible choice. Mm-hmm.
Just with that, they'll say
Because I created an augmented.
oh, why?
Oh, because
it's
you just
just
put B of
extra,
1.
yeah,
Yeah, sorry.
You just complicated your life unnecessarily, but I mean, it's not wrong. It's just extra work.
Yeah.
The moment you have extra work in the code, you're using extra space for errors.
No, but otherwise it looks.
This one extra division. It uses some extra error. And that generalization is already there. Help you all think a little. If you're already working on something, just keep working. If you're stuck thinking, when I see a formula like this,
Basically, I need to compute, this is problem with n. I have a vector with n values. So essentially for I is equal to 1 to n, I want to compute my x of I, which is my new value of x of I. Or this is my x of I to the k plus 1. And this formula tells me that it's b of I minus some sort of sum. So I'm just going to call it sum. And I'm using some m because, or some am or something. I need something different from the word sum because word sum is a function. Whoa, hi. And that is divided by a of I. And this is essentially this piece of code. My only problem is that I haven't computed this sum. Is that correct? So I'm kind of working on a skeleton of the code. Is this part clear? Right. Great. So now I just need to compute that sum. Whenever I'm computing sum, one thing I know is that I start from 0. That's like 2 points on exam right there. So write what you know. That's my... Okay? Just give me 2 minutes. So this is a sum from j is equal to 1 to n, and I have to be different from I. From j is equal to 1 to n. And update my sum is previous sum plus a of ij times x0 of j. So x0 of j is my previous. It's this xjk. And the only thing I have to make sure is that do this if I is different from j. So when stuck, do things step by step of what you know. Try to logically kind of fill in. Or just leave space, especially if you're working on an exam and you're like quick and you know that you're not going to necessarily complete. Leave space, say, oh, here I compute that sum, and then write me the rest of the code. It's a good strategy, but it's a good strategy for writing the code because you cannot think of everything at the same time. You have to kind of go step by step. So we computed the new x. I already computed the error. And how am I going to update x0?
X0 equals X.
That's it. Code done. No, it's not done. It needs to be tested, but I'll leave that part to you. So recap, set your initial guess, or maybe put it as an input to the function. Set initial error so that you actually can start the loop. Set the tolerance. This is up to you what the tolerance will be, unless the problem is saying what it should be. While error is larger than that tolerance, let's compute new x. This for loop essentially executes this. Then recompute the error and update x0. And keep iterating until your error goes below tolerance. That's all. Now it's just testing, and that I'll leave to you. Good? Questions? So this is basically the logic of every iteration. And we have a whole lot of built in this. Everything that we knew already, how to compute the sums. We did that initially. This is why we were doing it, okay? We
have for loops, that's why we have while loop. We have error computation, vector norms. This kind of sums up everything that was done before. But if I just give you a method like this, you can program it regardless of knowing what the method is and what is it doing.
Okie dokie.